Today we're going to be talking about logarithms. In the warm-up, you saw a function that was called the Zilkowski function and you were looking for patterns. It's not actually the Zilkowski function, it's called a logarithm function, and the way it's written is with log, log, some subscript, so let's say 2 as the subscript, something inside of the logarithm, so let's say 8, and this is asking, what do I have to raise the base of 2 to get 8? And so the answer would be, I have to raise it to the third power. A logarithm just represents an exponent, and the exponent is 3 here that I would have to raise 2 to get 8. How I read this is log base 2 of 8 is equal to 3. That's how I read that statement that's written there. So that's just what we talked about what was talked about in the warm-up. And then for the first 2 learning targets, we are going to talk about how to convert between logarithmic form and exponential form. So first of all, a log is the inverse of an exponential. And so we can convert between the two by changing our inputs and our outputs. Our inputs and outputs switch. In an exponential function, we have some base raised to an exponent is equal to some answer. This would be an exponential equation or exponential form. So this would be my exponential form. And if I wanted to convert that to logarithmic form, I would write log, short for logarithm. I would write a subscript, and the subscript would be, in this case, b. It would be the base. What's inside of the logarithm would be the answer, usually the biggest number. And then what the logarithm outputs is the exponent. So this is how you convert. And you can go from this one to this one, or this one to this one. It doesn't matter the direction you need to go. You can convert between the two. I like to use b for base, e for exponent, and a for answer because when I write it in logarithmic form, I can see the order that I see these things in is b, a, e. How I remember this order in the log form is that I think log is bay. It has to come before anything else this week because logarithms are kind of hard and you need to focus on them and study them so that you do well on your test. So if you remember log is bay, you can remember the order that you see it in the logarithm equation. That is that. And then for the third learning target, we're talking about evaluating logs. I'm just gonna move this over. Oh, and again, this is the logarithmic form. Evaluating logs. Sometimes, like in the warm-up, you can do it without a calculator. So you can evaluate some logs without a calculator. When you're evaluating a log, you're looking for the exponent. And you can do that easy if it's a well-known base and answer that you have. So for example, if I wanted to do log base 8 of 64, this is asking what do I have to raise 8 to get 64? That's a well-known answer. the answer is the exponent of 2. I have to raise a to the second power to get 64. But some logs you're going to need your calculator for because it's not that easy. So you'll need a calculator. And an example of one that you would need a calculator would be something like log base 3 of 2.7. This is some, oopsies. So this is asking, what power do I have to raise? Let's see. This is asking, what power do I have to raise 3 to get 2.7? That's not something I can do in my head, so I would need to use a calculator for it. In your calculator, there are 2 buttons that are for logarithms. One of them says log, and the other one says ln. These are the 2 that are in your calculator. Since logarithms are the inverse of exponential functions, they all have different bases, and there are infinite parents for logarithms, or infinite bases for logarithms that you can have. We only have 2 of those bases in our calculator. One is base 10 and the other is base e. So we need to convert our logarithm, however it's written, into base 10 or base e so that we can use our calculator. So if we see some logarithm with a base of b and something inside of a, we will, in order to put it in our calculator, do a fraction or a ratio where we would do log base 10 of a over log base 10 of b. So we just put the answer into the top logarithm and the base in the bottom logarithm, b for base, b for bottom. So we make a ratio. And that'll give us our answer if we put it in our calculator like that. We can also use ln instead. This is another logarithm. It's base e. And that's also in our calculator. And you do the same thing and you'll get the same answer. This is equivalent to this. So that's how you use your calculator. And then that brings me to my next point, which is common logs. Common logs, I guess this is not part of that. Common logs are the 2 that are in your calculator. It's the one that's log base 10, or you'll just see it in your calculator as log. This means log base 10. If you do not see a base on a problem in your homework or anywhere in this unit, it means it's base 10. So just like if you don't see a 1 in front of an equation, you still know it's there. If you do not see any number as the base, that means the base is 10. That one is in your calculator, and so is log or ln, which is log base e. So these are the 2 that you're going to see in your calculator, and those are the ones that you're going to use when you need to use your calculator. E, if you don't know what it is just some irrational number. It's like pi. It comes naturally in the world. It's 2.718. It's just, if you have an E button on your calculator, if you click it and make it to the first power, you'll see that's the number that you get. This is called the natural log. If you see that word anywhere, that's what it means. You're talking about ln. For the 4th learning target, we are going to talk about how logs and exponential functions undo each other. Before I talk about that, I want to talk about how log is similar to sine, cosine, and tangent. So you put something in, we don't say cosine, or we don't write out cosine when we're writing an equation with cosine. We just write cos, or cos. And then we put an angle inside of those ratios that we have. It's very similar. So log is similar to sine, cosine, and tangent. And for example, maybe I have sine of theta is equal to 4/7. So I have what the ratio is, and I need to find the angle. If that's the case, I have to go backwards to get to the angle by itself, and the only way I can do that is undoing sine to the theta. And how I undo sine is I take sine inverse. So if I wanted to undo this sine, I could take sine inverse of the left-hand side, and that would cross out because they're inverses of each other. So you could cross out the sine inverse and the sine because they're inverses, and you'll be left with just the angle that you're looking for. On the other side, you also have to take sine inverse of that side. Whatever you do to one side, you have to do to the other. So you take sine inverse of 4/7, and you could put this in your calculator and get an answer for what angle we're talking about. That is the same thing that you can do with exponentials and logarithms because they're inverses of each other, so they undo each other. So a log undoes an exponential with the same base. It has to have the same base. They're inverse operations. And vice versa. You can undo an exponential with a log, or a log with an exponential. So for example, if I had b raised to the x power on one side of my equation, and I wanted to get back to x by itself, so I wanted to solve for x, I could take log with the same base of that side. If I take log base b of b to the x power, the log base b and the b cancel each other out, and I'd be left with just x. Same with if I had a logarithm with a base of b, and inside of that logarithm was x, then I could, if I wanted to undo what was happening to the x, so undo the log base b, I would use the exponential with a base of b. So I would take the base of b and raise it to this power so that I could cross out the base of b and the log base b, and I would be left with just x. So we'll do some examples. The first question I have is I want to rewrite each exponential equation in logarithmic form and evaluate using technology. So this problem, 2 to the x power is equal to 31.6. I can't do that in my head. I can't think of which exponent I need to raise to get 31.6 because it's not a well-known answer. And it's going to be some decimal, and I can't do that in my head. So what I want to do is rewrite this in logarithmic form. So I'm going to write log, L-O-G, and I'm going to decide what's my subscript, what goes inside, and what goes on the other side. Well, my subscript should always be my base, so 2 should be there as my subscript. Inside of the logarithm, I should always put my answer. This is my answer to the exponential form or exponential equation that I have. So 31.6 goes there, and that is equal to my exponent. A logarithm is always going to be equal to an exponent, and my exponent here is x. This I can't put in my calculator because it has a base of 2, so I have to change the base. I'm using that change of base formula where I do log base 10 of 31.6 divided by log base 10 of 2. This I can put in my calculator and get an answer, and when I do that in my calculator, I'm going to get an answer of 4.982. So this is my answer for what I have to raise to get 31.6. I'll do it again with this one here. I want to change to log form. So I'm going to write log for to turn it into a logarithm. The subscript is always the base, which is 8.4. Inside of the logarithm is my answer, which to the exponential equation is 2,340. It's usually your biggest number, usually, not always. You can have if you have a fraction exponent, it would be different. And then you have your exponent on the other side, x. This is the exponential equation rewritten in logarithmic form. Now, I can solve this. I couldn't solve it before because I couldn't do that problem in my head. And if I can't solve a problem in exponential form, what I'm going to do is convert it to logarithmic form and vice versa. If I can't solve it in log form, I'm going to change it to exponential form. As long as I'm only missing one thing, I will be able to solve in one of the forms. I can solve this in logarithmic form because I can put this into my calculator. Not exactly how it's written, but I can convert the base to base e, so I can do ln over ln, put the answer in the top and the base in the bottom. And when I do that in my calculator, I should get an answer of, I have to raise 8.4 to the 3.645 power to get 2,340. Then I want to rewrite e to the x power is equal to 7.8 in logarithmic form and evaluate using technology. Well, again, I'm changing to log form, so I'm going to write log. The base is e, so that's the subscript of my logarithm form. Inside of the logarithm, I'm putting my answer, which is 7.8, the answer to the exponential equation. And then on the other side, I put the exponent, which is x. This, I could use the change of base formula if I wanted to, but even easier, I should recognize that log base e is the same thing as ln, which is in my calculator. So I can do ln of 7.8 and get my answer. And then that would mean my answer is I have to raise e to the 2.054 power to get 7.8. The next question is to solve log base 3 of 2x minus 5 equals 4 for x. I'm only missing one thing, so I should be able to solve this, but I can't solve it in log form. If I can't solve something in log form, I'm going to convert it to exponential form. So instead of writing it in log form, I'm going to write exponential form. I start with my base, which is 3. I raise that to the exponent I have, which is 4. And I'm going to set that equal to the answer, which is 2x minus 5, and then solve this problem. I can solve this problem. 3 to the 4th power is 81, and this is something I've seen many times before, a linear equation. I'm going to add 5 on both sides, not a linear equation, but a one variable equation. I'm going to add 5 on both sides, and I mean, it is a linear equation also, but I have 2x is equal to 86 then, divide both sides by 2, x is equal to 43. And that is my answer. So I have to have x, in order for this statement to be true, x needs to be 43, because that would make the inside 81. An initial deposit of $200 is invested in a bank account at 6.5% interest, compounded annually. How long will it take until the balance grows to 400? It says compounded, so I should be using the formula that's 1 plus r over n to the nt power. But if it says annually, that means n is equal to 1. So this and this aren't really necessary to have, and I can just write y equals a times 1 plus r to the t power. This is another equation that we know when we have percent rate of change and growth. This is the one we're using. And this is when the interest is applied only one time per time period, which is what's happening once per year, which is another reason why we're using this formula. You can use this formula, it's just you're plugging in n is equal to 1. A is, in this case, my initial value, which is $200. The R is 6.5% converted to a decimal, so 0.065. I'm just gonna write 0.065. And then the 400 that I see here is actually, it's not my exponent like I'm used to my other number being. It's telling me how much the bank account's gonna grow to. And that is my y value actually. So when I plug these things into this equation, I'm gonna have 400 is equal to 200 times, I have 1 plus r, which is 1.065, to the t power, and I need to solve for what t is. I'm going to first, to get t by itself, I'm going to divide both sides by 200. When I do that, I'm going to isolate the base raised to the exponent by itself. 1.065 to the t power is equal to 2. I have 1.065 to the, I'm going to change it to x because I like x better, is equal to 2. Right, I want to get this x by itself. Right now I have an exponential on the left-hand side. To undo an exponential, I can take the log with the same base. If I take the log base 1.065 of the left-hand side, the 1.65 and the log 1.065 is going to go away, and I'm going to be left with just x, which is what I'm trying to solve for. If I do that on the left-hand side, I have to do that on the right-hand side, and then I can cross this out and just be left with x, and that's equal to, I have to change this base to fit in my calculator, so I would do log of 2 divided by log of 1.065. And if I do that in my calculator, I should get, about 11 years. And then the last one, a new iPhone is purchased for $799. The value of the iPhone decreases by 33% each year. After how many years will the iPhone be worth $100? I'm going to be using the depreciation or decay formula that when I have a percent rate of change. So y equals a times 1 minus r to the t, it's to the x power. And then I'm going to plug in the information I have. A is going to be $799, or let me write the whole thing out. A is $799, R is 0.33, so I put 1 minus 0.33 or 0.67 inside of parentheses total. I don't know what the exponent is, but I do know that the final cost, or what it's worth, will be $100, and that's the y. I'm solving, my unknown is the exponent, which means I'm gonna have to use a logarithm to solve this problem. The first thing I'm gonna do is divide everything by 799, and I'll get then 0.67 to the x power is equal to, it's 0.125 rounded. I want to undo this exponential on the left-hand side, this exponential of, or this base of 0.67, so I could get to the x by itself, and in order to do that, I have to take the log of 0.67 of this side, and I have to do the same thing on the other side. So I'm gonna rewrite this like this. This is 0.67 to the x power. This crosses out and this crosses out. I'm left with just x is equal to this. I put this in my calculator by doing, I could do ln of 0.125 over ln of 0.67, and I get an answer, which is 5.19 years.